they imply substitution nucleophilic, unimolecular and substitution nucleophilic, bimolecular. And so the rates are dependent. In one case, we only for the substrate. So essentially the way we describe the reaction, we have substrate. And the substrate eventually turns into an electrophile. So it becomes an electrophile or electron-seeking reagent, which is being attacked by a nucleophile. Or nucleus-seeking reagent. Nucleus is actually positively charged, that's why you call it a nucleophile. So they are typically electron-rich agent that would attack. And then we get the product from that. And what we have seen is there is a pattern of how the reactivity is being influenced both by the nucleophile and also by the substrate. So if we start with the tertiary, let me give you have the basic reaction is ROH, where ROH is the substrate, and the nucleophile, which would be the hydrogen halide, X is the halide. And R is an alkene. And that is converted to an alkene halide, Rx, plus water. And in this process, we learn that when X is I, which works best, better than Br, better than Cl, and chlorine does not react very well. That's the pattern we see. Another pattern is the R is the alkyl group when we have a tertiary. That works better than secondary. And primary and methyl are particularly bad in this reaction. And when we look at the energetics of those reactions, what we typically see is that if you have this is a typical reaction where the first step is actually energetically favorable, and it's a small energy demand, which is the protonation, EA1, protonation of the alcohol. Now let's just try HBr. So it forms a protonated species plus Br minus. And we are not showing all the electrons of Br. The second step is the most critical one, which is the high energy demand, and therefore that goes to a cation, which breaks down this bond between carbon and oxygen. So this is the red determining state. This is EA2. And then it goes to the product, which is EA3, and goes to now on these states, this step is actually exothermic. The second step is strongly endothermic. needs energy in order for them to get to the high level. Now, this is the reaction typically we know as SN1. And in the SN1 mechanism, what happens is, if you change the substrate from tertiary to secondary, then what happens is, let's give you another one. All we need to do is change the substrate from this to isopropyl. And then the first step remains about the same. The second step, the energy demand goes up because the secondary cation is actually harder to heat. And likewise, if you go to the primary, then let's say CH3, CH2OH. That will have a much higher energy demand. This second state is even higher. So what often happens that these reactions go reasonably well at room temperature with a tertiary, then you need to heat it up in order to carry out the secondary. And for the primary, the energy demand is so high that it would change the mechanism from SN1 to SN2. So for typically, as I mentioned, the tertiary and secondary would go through SN1 mechanism, and primary and methyl will change the mechanism to SN2. And how does the SN2 happen? In SN2, essentially the second and the third state are combined together. So if you want to understand the energy mix of the SN2 process, that would really, the first step is the same. And at this stage now our OH, breaking of this bond between R and O becomes so difficult that it needs a push from the anion, which is Br minus in this case, that attacks this, breaks this bond. And so now both states happen in one, gets to the final product of RBr plus H2. And that's why, however, you have to remember that this is still a higher energy needed compared to a tertiary cation, and therefore it is still more difficult, but it is by changing the mechanism, it becomes a little bit better than what would be if it followed entirely the similar pattern. Now, there are a couple other things that we can actually relate to the structure. In each case, we have a transition state involved. So let me go back to the previous model. So this is TS1. This is the TS2. And what would be the transition state structure? And there are some predictions to the structure that you can think of. One would be that the transition state structure is between the two stages, starting material and the end product. It's somewhere in between. But is it close to the starting material or the product? That was predicted by George Hammond, who suggested that, which is known as Hammond postulate. If the energies of two states are similar, they are structures are also similar. Here also suggested that if they are very dissimilar, they are also, the structures will also be very different from the structure that they are closer to, remember. Okay, so now let's see what would be the transition state 2 structure. Now this is far from the carbonation structure that we are generating from here. Okay, the structure will be very different from this one because energetically it's very different. It is closer to the carbonation, so it is closer to the structure of this as well. So we can kind of draw the structure using, rather than complete bonds, a broken bond. So the broken bond, how we would draw it, it's like C, okay? And it is connected partially at this point to the oxygen, and the 2 hydrogens are attached to that. This one has a delta plus, and this one also has a delta plus, because the positive charge that was entirely on oxygen when we started, it all moved to the carbon after the bond is broken. So this intermediate structure, which is the transition structure at this stage, would have a partial bond between the carbon and oxygen, and the positive charge is distributed between oxygen and carbon. Eventually, when it gets to the carbonation, all of this positive charge will move to this carbon, and the bond will be completely broken. So there will be no dash between them, and so the oxygen and carbon will be completely separated at this stage. But until that happened, this is really the structure of the transition state. The irony of this type of postulate is that you can never catch the structure. There is no way to actually find the structure, but there are indirect experiments that can prove this. All right, so what we showed there is that the way to convert an alcohol to an alkyl halide. But because the energy demands are high for the primary and the methyl, there are often other methods where different. Normally, this is done for primary and methyl because the tertiary goes very well with the hydrogen halide. But in order to make the alkyl halide, such as chlorides, can be made, thionyl chloride is SO2Cl2. And an advantage of this reagent is that it does not follow the typical SN1 or SN2 pattern. What it does is like you have, let's say, an ROH. If you treat it with thionyl chloride, which is, sorry, not SO, thionyl chloride, SOCl2. So the alcohol can still attack the sulfur, okay, and it displaces one of the chlorine. So it generates ROSCl, and then one of the chlorine is displaced as Cl minus. So once this is formed, the chlorine can attack the R group directly and displace this, generating RCl. essentially that combines with the hydrogen to make the hydrogen chloride. And in this process, usually, if you add some pyridine, the reaction goes faster. Okay, pyridine can be added. Pyridine is a base. Acts as a catalyst and solvent. So typically, these reactions are typically done with primary and methyl groups, and not with secondary and tertiary, which goes very well with the hydrogen halide. And another reagent similar to that, if you want to make a bromide, is PBr3. So let's say you have propanol, you can use PBr3 to make it the corresponding bromide. And typically when we use an arrow indicating a reagent being used, normally we don't care about the stoichiometry. You don't have to actually make a balanced equation, but you really want to concentrate in the organic material that is generated. So this is a method of converting an alcohol to a bromide. Likewise, the previous method using thionyl chloride will write the same thing. We can use SOCl2 plus pyridine to make the corresponding chloride. All right, any question? That kind of concludes the fourth chapter. Yeah, you have a question?
I just wondered if beyond our scope, I guess that's fine, but how pyridine is able to catalyze that reaction?
Okay, the way normally pyridine catalyzes is that pyridine actually forms another complex with it and acts as a living group. Okay, we're not going to go through too much with that. All right, so let me kind of go back on chapter 3, because there are some confusion, as I understand, for some people did not follow or confuse the cis and trans and axial and equatorial, all of this. So I wanted to clarify those. Normally, when you have a structure, any structure for that matter, but let's say a cyclohexane structure, and you have one bond with something that is indicated as a wedge, and another bond with a dash, and a third one, let's say, with a wedge. What that really means is that the relationship between them, in terms of cis or trans, whether they're on the same side or different side. So the relationship between these two, let's say it's X, Y, and Z. Then we can see that Y and Z, the relationship between them is trans. And that's why we're using wedge in one case and dash in another case. If they're both wedge or both dash, then they would imply that they would be, their relationship is essentially cis. Like X and Y, the relationship between them is cis. And by the same token, if X and Z is also trans. So once that's clear, a lot of things will become very clear as well. Now, cis and trans can be used in many other cases as well. In this case, we are using it like this. But if you have a double bond, then whether they're on the same side or different side, that's what indicates the groups. So, in a double bond, let's say you have a methyl group here, another methyl group here, then of course the same side, this is 6. Okay. If they're on the opposite side, then we'll call them trans. This is trans. So 6 and trans can be used essentially based on the plane, whether they're on the same side or opposite side. Now, if we start with this one and do this, actually let me give you an example of a structure of glucose. One of the structure of glucose, it's a 6-member dinos, peroxide. This is actually one part of your problem.
What is that?
Point towards me. One of the structures. They are given 2 different structures. One of them is this, where you have an OH group here, followed by another OH. 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 Then CH2OH. So now let's convert it to the chair form. So if we do in chair form, then one of the corner would be occupied with oxygen. And let's draw that. So we have converted this hexagon to a chair form. Now, we can start with any one of the sides, but let's start from here. Let's be here. The relationship between this OH and this OH is trans, right? One way, one back. Since it's trans, and we know trans diaxial is much higher energy than trans diequatorial. So let's start with equatorial. We put this as equatorial OH, which is this side. Then the other one would also be equatorial. Now between this one and this one, again, it's a relationship of trans. So again, this would be equatorial. This one and this one would also be trans, and therefore equatorial. Between this one and this one also is trans, so that's going to be equatorial. And that is the only one that's CH2OH, all others are OH. So this one, therefore, we draw them like CH2OH. So this structure and this structure essentially are the same. One is converted to the chair. Okay. And there are some problems in the handout as well. We'll go over that. Any question on this? Yes?
Can you find a substitute like that in your most stable state?
Right. Because the other one is when it would be extremely unstable, all action. Yeah.
A good idea to start with the bulkiest constituent or that?
You can do that. You can do that. Yes. Repeat the question.
Why was it diequatorial?
Okay, the diequatorial actually, I have to show you the model. Can I borrow yours? I didn't bring it. Okay, so the reason it's diequatorial is that diaxial, these two are opposite sides with respect to this plane, right? Therefore, they are trans. Likewise, these two also are on the different side. They're trans. So only when one axial, one equatorial in 1, 2, then they would become 6. Okay. And again, I emphasize that 1, 2, and 1, 4 relationship are identical, exactly the same way these two are. Again, this is 1, 2, 3, 4. They are opposite sides, therefore they are trans. And these two are also trans. And so same relationship, 1, 2, and 1, 4. 1, 3 is exactly reverse. Thank you. All right, so go over the homework problem that I gave you? This is practice quiz.
Oh, you email this right first? Huh? You email this right first, is it? Yeah. Or different one?
Okay, so in the practice quiz, therefore, following the
Yeah.
same protocol, the relationship between the two structures. The first one is this is equatorial methyl group, followed by this methyl group, which is at the 2 position, is this is 1, 2, 3, and 4. The 2 position methyl group is axial, and the methyl group at the 4 position is equatorial. And when we go from this one to the other structure, again, this one is equatorial, this one too is equatorial, and the 4th one is also equatorial. So as you can see, you have equatorial, axial, equatorial methyl group, and the other one is all equatorial methyl group. So there's no way you can flip them to get to the other structure, right? Which means that they must be stereoisomers. Because the only way you can go from one to another would be if you flip this one, these two become axial, this will become equatorial. That's not the same structure as this one. So there is no way you can go from one to another, and therefore they must be stereoisomers. So E is the answer. This one is again the same way you convert them. That's 1, 2, and 4 again, and the relationship between 1, 2 is cis, and 2 and 4 is also cis. So when you do the chair form, if they're cis, then one would be axial, one would be equatorial, and arbitrarily we can just select one. Let's say we do this one is equatorial, the other one is axial. So 1, 2, and the 4th position now, because they're cis, they have to be the same, diaxial or diequatorial. So this is going to be axial, which means that this is a somewhat unstable arrangement because 2 methyls are axial, they're going to flip to the other form where the 1 position would become axial and 2 and 4 position would become equatorial.
Can you move it towards the side?
But
The paper, can you? Yeah.
so now, as you can see, these all methyl groups are equatorial. That's not right. Equatorial methyl groups at C1 and C2 and axial at C4. Okay, that's also not correct. Equatorial methyl groups at C1 and C4. But which ones? So this is 1, 2, and 4. So we have equatorial methyl groups at C1, axial at C1. So this is actually D is the answer, right? What is the IUPAC name of the following compound? The IUPAC name, again, cis and trans is based on that relationship. So in this case, this is going to be the cyclohexanol, and then you decide what the 3rd position group is. 3 position has a methyl, and the relationship again, 1 axial, 1 equatorial, there must be trans, right? Because if you have cis relationship in case of 1, 2, and 1, 4, that's when you have 1 axial, 1 equatorial. In case of, sorry, this is actually a trans relationship. Because it's 1, 3. There's three levels, yeah. Okay, question 4, asking what is the estimated diametral angle between the two method groups on the structure shown below. So one method group is here, the other method group is here. So you need to look at the plane that going through this carbon, and this carbon. That is one plane. And another plane would be this carbon, and this method carbon. So based on that, you can see that angle is about 60 degrees. What is the IUPAC name of the compound below? And again, you have to consider what the OH group is. That's the most important one. So this is therefore 1, 2, 3, 4, 5. Then the method group is 6. So this is really a hexanol, but it's 2 hexanol. Then you have 2 other method groups at the 5 position. So it's 5, 5, 11, and 2 hexanol. Rank the following 3 compounds in order of increasing boiling point. The boiling point, as we know, typically when you have OH group, because of hydrogen bonding, they have the highest boiling point compared to all the others. So the hydrogen bonding is the most important one in terms of determining most important for boiling point, melting point, and so forth. So in this case, this is the alcohol. Therefore, that would be the highest boiling point, followed by the one that has oxygen in the ether. This oxygen infers that dipole-dipole interaction, but not as strong as the alcohol. So this is number 1, this is number 2, and this is an alkane. Therefore, this is number 2. Okay, so increasing boiling point, therefore, we have to have A is the lowest, then C, followed by B, which is which of the following is most reactive with HBr? And again, it's important to recognize what kind of carbon they are attached to. So the carbon they are attached to, in this case, this carbon. In this case, this carbon. Third one is this one. The fourth one is this. And in order to figure out, this is therefore tertiary. This is secondary, this is primary, and this is methyl. Therefore, typically the most reactive would be the tertiary, which is D. Identify the tertiary alcohols. Again, you look at the specific carbon to which the OH group is attached. This one, and this one. So again, in this case, this is a secondary, this is also a secondary, and this is tertiary. So that is the most reactive one. And this is the tertiary alcohol, so this is only C. What is the nucleophile in the following substitution reaction? This is the example that we gave you, and the nucleophile, of course, is the Br minus, which is 3. Arrange the following carbocations in order of their decreasing stabilities. Most stable first. So again, we look for the tertiary. This one is a tertiary carbon. This is primary carbon. And this one is a secondary carbon. Okay, so if we do decreasing stabilities, then A is the best, followed by C, and then B. Okay, A, C, B, which is C. Okay? So the quiz would be very similar to this one, similar type of question. If you read, it would be, I didn't start to get to go to chapter So we'll base it on the reactor free energy. All right? See you one minute.